So let's move on to the next topics in linear classification, which is logistic regression. Okay, here it's kind of weird thing that you find is that you have regression in the name. So you might think it's a regression, it's a regression problems. No, logistic regression is classification algorithm. Don't be confused. So name is logistic regression, but it's again it's like the SVM, it's a linear classifier. Its name is very weird. It says classification problems says have regression on it, and you guys probably have no idea what the logistic is. I'm gonna explain why the people like to name this method is logistic and the regression later on. Okay, so perceptron, SVM, two algorithms that we cover is make use of sign of data. Do not use the distance. Remember it, think about it. Use of sign, whether let's say it's plus or minus, whether it's a positive or negative. Those are the information that we utilize it. And we already showed there's some drawbacks. So we have further enhancement. Is the idea is that we come up with this SVM. It's use distance, the margins, minimize the distance. And so in that case, let me show you how many data points in SVM is the most critical one. How many data points? Probably these two. The margins, which is the closest data points for each class to the boundary is the most critical one. So I will say distance from two closest data points. That's the information that we used or that we considered to build up the SVM. But the natural way to go, the next step is that why don't we use entire data points? Why don't we? We want to use distance information from all the data points here. Instead of two, I will say all the data points. Here, SVM, I use only this two data points is two distance, which is margins. And I guess probably if you have a more data set, I want to utilize all the distance like that. That's the basic starting point. We might have further chance, room to improve. So this is going to say is logistic regressions. So let's assume that since logistic regression is going to consider the entire data points, then as opposed to SVM is going to use only two data points. Hope that that the mechanism is going to better better classifiers. Let's see. The motivation is that for logistic regression, suppose we have only two data points. So this is first class and the second class. You use circles and squared, and omega is that directions. This is boundaries. Which one is good boundaries? Number one or number two? Which one is better? Number one is kind of the classification boundary is kind of located in the middle, and as opposed to the number two is kind of more toward to circle points. This point, if you think about the distance, here is kind of equal. Which one's better for classification boundary point of view? Number one or number two?
1.
Number one, right? Number one. So we want, I mean, I don't need to explain why number one is better than number two. We want to have boundaries put in the middle as possible as we can. Okay, then let's see. We know how to compute the distance. Let's say we can compute distance. Now we can compute distance as well. I mean, these are the different, but here, compute that one. And say, I don't know what, but say, somehow let's do summations. Let's do summation. And this is sine the distance. That's why I want to put the absolute. I did that. And in second case, I can do same thing and do summations. So which one is bigger? Or which one is smaller? Which one? Or those two are the same? I think if these two are parallel, I mean, I guess are the same, right? So if you compute, so we know how to compute the distance from all the data points and do summations, and those two are going to be the same. So we cannot pick one is better than two based on the value of summations, because it's going to be the same. So it fails. Now, I mean, if you do summations and say that it's not good, then the next thing, probably the natural way of the things that come up with is probably multiplications or product. Let's do multiplication. Now, which one is bigger? Which one is bigger? I can give you some, let's say these are the like, and if you do, I mean, this is just examples to illustrate, like 4, if you do 3. So which one's bigger? So using that simple examples, the insight that we can, or the hypothesis that we can have is that compute all the distance and take the absolute values and do multiplications, and since we say that this one is better, probably the larger value of multiplication is going to give us a better classification boundaries. That's kind of the hypothesis that we can come up with. What do you think? What do you think?
Sorry, can we do a subtraction?
I mean, yeah, we can do, but I mean, don't worry about the other things like just we can do
like if we get 0, it's better. H1 minus H2, and if we got 0,
I see. But the idea is that okay. So you said that H1 minus H2 probably is 0 is better, right? I mean, this one H2 minus H1 probably is 2. So we want to minimize that one.
Exactly.
Oh, that's good. That's good. But the problem is what do I say? That's a good point. But okay, let's I think what you mean by that. So let's keep that in mind, and let's don't keep these things aside and let's move on to that way. Okay, I will go back to that point. And I want to see whether this is true or not. And remember, I guess you guys know this when A and B is like that. You guys know, look familiar this kind of inequality equations, inequalities, or no? This is arithmetic mean or average, and these are the geometric. So these are the, let me see, like that. If we take the square because it's all positive. So this is true. This is true. So this is true sentence, true inequality. And so thing is that if you do this kind of calculations, this value is always smaller than or equal to that, right? But I said the summation is not always constant. And when the equality holds, A equal to B, right? That means this one and this is constant. If you do A plus B is the summation is a constant, and this is a C constant, which is upper limit. And if you do multiplications already smaller than C, the maximum value that we can have is when A is equal to B, right? That means I want to maximize these things. Then getting close to, let's erase that. I want to maximize these multiplications. And when it's maximized it, these two are equal, which means the distance and the classification boundaries tends to put in the middle. You see what I'm trying to convince you guys? So the idea is that all the distance that we can compute it and do multiplications, and I want to maximize it based on the different omegas. If you find that maximum point, in that moment, the omegas gonna give us the linear boundaries, which believe that tends to put that boundaries in the middle of two data points in groups or classes. Does it make sense? Using that arithmetic and geometric inequalities, you can get some insight or ideas. Now we start from two data points. Now we can have more than that. And this inequality is true. So the idea is that we utilize all the distance and what kind of calculation that you have to have in objective functions, we have to do this. We want to maximize all the product or multiplication of absolute value of distance. And again, it's maximizing the optimization problem. What's the decision variables is omega. Omega is the same as decision boundaries because we can get, if the omega is given, we can, it's orthogonal. We can get it. So we start from two data points. Now I kind of generalized it. And the only message that I want to give you at this moment is that for logistic regression, which is another linear classification algorithm, utilize all the distance. How do you do the optimization, or is that do multiplication of those the distance and I want to find the omegas that such that to maximize those the multiplications. And we know that that's the formula of the any data points H is given by G of X omegas. So we want that one, and G of X is omega transpose X, and it's related to omega is omega. So kind of you can assume that H is omega transpose X related to. We kind of, it's not mathematically rigorous, but roughly speaking, the optimization of maximize it tends to position in the hyperplane in the middle of two classes. And we know that H is related to omegas. So omega is decision variable that we have. And let me ask these questions, and then I'm gonna finish that. Suppose we have SVM, and we have another one, logistic regressions. I mean, this now is the middle of explaining of what the logistic regression is. And with these, the two classes of data points on left and right side are the same. And suppose we have new outliers. New outliers. The question is, for SVM, if we include these new outliers, that's gonna change? That's the first question. And the second question is, for logistic regressions, the new classification boundary is gonna be the same or change if we take into another outlier data points into the considerations. That's the question that we have. If you are able to answer that, probably you have right understanding of what the SVM and what the logistic regressions are. And think about it, probably I'm gonna give you the answers in the next time, which is Thursday. Right? That's the big difference, and I guess this is right examples to see the difference and try to understand right mechanisms on the SVM logistic regressions. Okay, with that, and I will stop the recordings here.